Today, we're diving into the fascinating world of natural language processing, commonly known as NLP. It's all about creating a bridge between how humans communicate and how computers understand. Before computers can understand human language, we need to perform some essential text preprocessing steps. These steps are crucial for preparing raw text data, making it ready for computer understanding and analysis. Our first key step in text preprocessing is called tokenization, a fundamental concept in NLP. Tokenization involves breaking down a larger piece of text into much smaller, more manageable units, which we call tokens. These tokens can actually be individual words, entire sentences, or even single characters, depending on our needs. Next up, we have stemming, another important technique used to normalize words in text data. Stemming works by reducing words to their core base or root form, simplifying their representation. It uses heuristic rules, meaning the output might not always be a grammatically valid word, which is important to remember. Then we have lemmatization, which is similar to stemming but with a more sophisticated approach. Lemmatization aims to reduce words to their dictionary or base form, known as the lemma. Crucially, it's context-aware, ensuring the output is always a grammatically valid and meaningful word. The ultimate goal is to produce output that sounds and reads just like human-created language. Let's delve deeper into why tokenization is so incredibly important in natural language processing. It's all about effectively breaking down large amounts of text into smaller, more manageable units for analysis. Tokenization enables computers to efficiently process text, transforming it into manageable pieces that are ready for detailed analysis. Furthermore, it's a vital step in converting raw text into a numerical format, which is essential for most NLP tasks. Next, we have stemming, which helps standardize words by reducing them to a base form. Stemming reduces words to their root by chopping off prefixes or suffixes, though the result might not be a valid word. Following that, lemmatization reduces words to their dictionary form, considering context and part of speech. Lemmatization reduces words to their valid dictionary form, or lemma, always considering their context and part of speech. Now, let's explore the key differences between stemming and lemmatization, two common word normalization techniques. Both are crucial for normalizing words, but they achieve this goal in slightly different ways. First, let's look at stemming, often considered the more straightforward of the two methods. Stemming is generally a simpler and much faster process, making it efficient for large datasets. It works by removing prefixes or suffixes from words based on a set of predefined heuristic rules. Remember, a characteristic of stemming is that its output might not always be a real, grammatically correct word. For example, the word running would be reduced to run through the stemming process. On the other hand, lemmatization offers a more refined and accurate approach to word normalization. It is generally more accurate because it's context-aware, understanding the word's meaning. Lemmatization uses a dictionary and considers the word's part of speech to find its true base form. Consequently, the output of lemmatization is always a valid and linguistically correct word. Today, we'll learn how to build a bag of words model, a fundamental concept in natural language processing. We'll explore the simple, yet powerful steps involved in representing text data numerically for machine learning. First, you'll create a unique vocabulary, which is essentially a list of all distinct words found across your documents. Next, we represent each document based on the words from our vocabulary, ignoring their original order. Then, we count how often each word appears within every document, giving us its frequency. Finally, these counts are used to form sparse vectors, numerically encoding each document for analysis. Next, we have TF-IDF, which stands for Term Frequency Inverse Document Frequency, a more nuanced approach. TF-IDF assigns weights to words, considering their importance both within a document and across the entire collection. This method smartly gives more significant weight to words that are unique and distinctive. It also carefully accounts for how often a word appears across all documents, known as its overall document frequency. Now, let's dive into calculating TF-IDF, a crucial technique for understanding word importance in documents. Term frequency, or TF, measures how often a specific term appears in a particular document. Inverse document frequency, or IDF, assesses how unique or important a term is across all documents. The TF-IDF score combines these two measures to highlight words most relevant to a specific document. Here, W represents the specific word we are currently interested in analyzing, and D refers to the particular document we are examining at that moment. The numerator is simply the count of how many times the word W occurs within document D. The denominator is the total number of words present in that specific document D. Essentially, TF measures the local importance of a word by how frequently it appears in one document. A higher term frequency indicates that the word is more common and significant within that particular document. This metric helps us understand the importance of a word specifically within its document context. Now, let's move on to the inverse document frequency, or IDF, which considers global word importance. IDF for word W is the logarithm of the total documents divided by the number of documents containing W. Again, W denotes the specific word we are currently focusing on for our analysis. The total number of documents refers to the entire size of your document collection, or corpus. This is the count of how many documents in our collection contain the specific word W. IDF tells us how unique or common a word is when we consider all documents in our collection. It effectively reduces the importance of very common words, such as the or is. A higher IDF value indicates that the word is more unique, appearing in fewer documents across the corpus. Finally, we combine these two to get the TF-IDF score, representing overall word importance. The TF-IDF score for word W in document D is the product of its term frequency and inverse document frequency. This is the term frequency we just calculated for word W within document D, and this is the inverse document frequency we determined for the word W. The TF-IDF score effectively combines a word's local frequency with its global rarity. Therefore, a higher TF-IDF score signifies that a word is more important and relevant. This powerful score is widely used for tasks like information retrieval and various forms of text analysis. Let's explore the core application areas of natural language processing and its real-world impact. NLP is incredibly powerful for extracting valuable insights and understanding meaning from vast amounts of text data. Sentiment analysis determines the emotional tone of text, like whether a review is positive or negative. Text classification categorizes documents into predefined classes, such as labeling emails as spam or not spam. Spam detection uses NLP to identify and filter out unwanted junk mail from your inbox efficiently. Analyzing customer feedback with NLP helps businesses understand opinions and improve products or services. Next, fine-grained sentiment analysis provides a much more detailed emotional spectrum. It uses a scale, allowing us to capture nuances from very positive all the way to very negative. Finally, aspect-based sentiment analysis is highly specific and contextual. This method focuses on identifying sentiment expressed specifically towards particular features or aspects of a product or service. Today, we'll compare word to-vec and GloV, two prominent methods for creating meaningful word embeddings. These are different approaches that transform words into dense numerical vectors, capturing their semantic relationships. Let's now explore how BERT, a powerful transformer model, actually processes language to understand meaning. BERT uses bidirectional attention, considering left and right context, pre-trained and fine-tuned for diverse NLP tasks. Self-attention allows the model to focus on the most relevant words in a sequence when processing each word. Multi-head attention means the model learns multiple attention patterns, capturing different aspects of relationships between words. Positional encoding is crucial because it integrates information about the order of words into the model's understanding. The encoder-decoder architecture processes input sequences and then generates the desired output based on that understanding. Now, Let's recap and summarize the key natural language processing concepts we've covered today. Here are the essential takeaways, focusing on how we process text for effective NLP models. Remember, thorough text preprocessing is absolutely vital for building robust and accurate NLP models. Techniques like tokenization, stemming, and lemmatization are crucial steps to prepare your text data. Bag of words and TF-IDF are fundamental methods to convert raw text into numerical vectors for analysis. Key applications include sentiment analysis and text classification, helping us understand and categorize text. To wrap up our discussion on natural language processing, let's go over the key takeaways. Here are the most important points and concepts we've covered that you should remember. Remember, NLP empowers computers to truly understand, interpret, and generate human language effectively. Preprocessing steps like tokenization, stemming, and lemmatization are vital for preparing text data. Techniques such as bag of words and TF-IDF are used to vectorize text for machine learning models. Key NLP applications include sentiment analysis for opinions and text classification for categorizing documents. Word embeddings are powerful as they capture complex semantic relationships between words in a vector space. Lastly, advanced models like transformers and BERT utilize attention mechanisms for deep, contextualized language understanding.